Okay, let's jump back to y. Let's look at the second boundary condition for y. So I think we labeled that 2. And that boundary condition said that v at x comma a is equal to 0. So this one's slightly less obvious because now I'm not just plugging in 0 for y. I have a specific value where y is equal to a. And so again, to kind of translate that, I have y at a has to equal 0. But now don't forget that in step 1, we found that d is 0. So we're not gonna we're gonna take that into account already. So y at a is equal to c times sine of ka. Right? There's no more cosine because d is 0, and we're doing 0 times cosine. So that cosine term is gone away forever. And our boundary condition says that that has to be 0. And so there are two options here. Either c is 0 or sine ka is 0, right? If c is 0, think about what that's going to do to our whole problem. Remember that our v of x and y is x of x times y of y. And so if c is equal to 0, then that means my entire y function is 0. And if my entire y function is 0, this whole thing is 0. And so what you could say is that the whole thing's 0. But that's a stupid solution. So we're not going to do that. This gives you a trivial solution because everything is 0. Oops. Right? Certainly, I could just make everything 0, but that's not very interesting. So that means we just ignore that. We don't have to worry about that one. Instead, we have this sine of ka is equal to 0. So if we think about sine is going to oscillate, right? So when sine of theta is equal to 0, sine of theta is equal to 0 when theta is 0. Right? Sine of 0 is 0. And then if you think about sine, it's going to come back to 0. So when theta is pi, and 2 pi, and 3 pi, and so on and so forth. So whenever the thing inside the sine is a multiple of pi, then that sine will be 0. And that's what we want. So what this is telling me is that this will be 0 when ka is equal to n times pi, where n just equals 1, 2, 3, 4, etc. Note, I'm not using n equals 0, because if I use n equals 0, I'm just going to get the same exact thing as what we did over here. Because if n is 0, the whole thing is 0. Doesn't matter what value you get for x, it doesn't matter what value you plug in for y. You'll always get 0 there. So we don't use the 0. We only use the multiples of pi here. And so here, so we now have our k. Remember, we didn't know what k was from the very beginning, but now we know it's n pi divided by a. So n is just an integer, 1, 2, 3, 4, et cetera, et cetera. Pi is just a constant, and a is just the height of our little green strip. Okay. Okay, so let's write everything that we have so far. Let's just sort of check in where we're at. We have now x of x is equal to b e to the negative kx. And our y, actually, sorry, we literally just figured out what k was, and then I ignored it maliciously. So we can plug in now n pi over a for that one. And then y of y is equal to c times sine of n pi y over a. Okay, so remember we started off by multiplying these together. So let's just multiply the whole thing together. So far our v of x and y is equal to b times c times sine of n pi y over a times exponential negative n pi x over a. Okay. And so now b is made up. B is just a made up arbitrary constant. We have no idea what b is. C is a made up arbitrary constant. We have no idea what c is. And so b times c is also made up. I have no idea what b times c is. So since all of this is made up, we're just going to absorb them into one arbitrary constant. All right. Let's see. I already used a c. Let's use g. We'll use g. So I have one constant. Now I only need to figure out one thing now. I only need to figure out what g is. And obviously everything else is the same. Okay. So we have one more boundary condition to deal with. The last boundary condition was number, what did I write down for that one? Number 3, I think. And so this is going to be the trickiest one. We said that v at 0, comma y is equal to a constant v naught. Okay. And so if I apply that to our new kind of fully adjusted function here, what I end up with is g times sine of n pi y over a times e, sorry, this is an x up here, e to the negative n pi 0 over a. And so this is just g sine. And we're told that that equals v naught, a constant. So the problem is sine is going up and down, right? And our answer or our boundary condition says that it must be a constant. And so the problem is that, the problem is there is no single value. Sorry, my writing is getting worse. Come on. What's happening here? There we go. There is no single value of g that can make this equation work. So I can't just say g is equal to 20 or something, and this will all of a sudden work. So instead, we have to make an adjustment and say that we have this sign here. Remember, n has all these values, 1, 2, 3, 4, et cetera, right? And so in actuality, we don't just have one solution, we have infinite solutions, right? We have the solution where n is equal to 1. We have the solution where n is equal to 2, 3, 4, 5, et cetera, all the way down the line. And so instead of just picking one value of n and trying to solve for g, we're just going to use all of these solutions. And add them up. So whenever you're solving a differential equation, if you have multiple solutions, you can write a full solution as just adding up all of the solutions, just kind of like we did with the sine and cosine, right? Up here, we knew that sine was a possibility. We knew that cosine was a possibility, so we could just add them up.